Hey everyone, welcome back to Engineering Education. For this next problem, we have an RL series circuit, only this time with a unit step function as an input, and we're asked to find the output V out of t, or Y of t, given that L is equal to 1 Henry and the resistance is equal to 1 ohm. So, as always, pause the video, give it a shot, and we'll go over the answer in a bit. So we can solve this different ways. We can use convolution. We can also use just the Laplace transform, and the way I'm going to solve it is using the Laplace transform. If I can avoid doing integrals, I will definitely avoid it, and what we can do is we can turn this unit step into its Laplace transform equivalent, and same with the inductor, we can turn it into its Laplace transform equivalent, and then solve the circuit as we normally would using voltage divider, and then once we solve that circuit, we can take the inverse transform and get the answer back in its time domain. So if we go to the FE handbook here, we have a list of Laplace transforms. So this is page 34. And here we are given the Laplace transform of the unit step function at t is equal to 0. And it's equal to 1 over s. So we're going to write that down on the next page. So the unit step function u of t, its Laplace transform is 1 over s. And the Laplace transform of ZL, which is the impedance of this inductor here, is j omega L, where j omega is equal to s, so SL. And here we can just apply voltage divider. ZL is going to be equal to SL in the Laplace domain, and U of t is equal to 1 over s in the Laplace domain. So V out in the time domain is R over R plus ZL, multiplied this U of t in the time domain. And when we transform that into the Laplace domain, we get R over R plus, now this time SL, times U of t, which is 1 over s. And then we can plug in the values here. So V out in the Laplace domain is R is equal to 1. So remember, the Laplace transform doesn't affect resistance. Resistance is just a constant. So that's R is equal to 1 divided by 1 plus L is also equal to 1, so that's S, multiplied by 1 over S. And that gives us 1 over S plus 1. And so our answer is simply going to be the inverse Laplace of 1 over S plus 1. I say simply, but it's actually a little bit more involved than that. We're looking for a time domain function that takes this form of 1 over s times s plus 1. And so if we go back to the FE handbook, we can explore this chart some more, and we have 1 over s alpha right here. We have 1 over s plus alpha squared, but there is no function here, or no expression here that'll give us what we're looking for. And so what we have to do here is we have to do a partial fraction decomposition. And so that's what we're going to do here to get the final answer. And so the way we would do that, as a little side note here, so we have to do partial fractions. And we're doing partial fractions so that we can break up this this fraction into simpler fractions that hopefully have, easy Laplace transforms that we can just look up in the table. And so 1 over s plus 1 times s can be broken down into two parts. Some alpha over s plus some beta over s plus 1. And so if we can solve for alpha and beta, we can decompose this larger fraction here into two smaller portions that will have Laplace transforms. And so what we can do is we can multiply this whole thing by s times s plus 1, giving us 1 on this end. Alpha over s times that quantity gives us s plus 1 plus beta s. And we can distribute this alpha, so that'd be alpha s plus beta s. Okay? Once we've distributed it, we can group these terms here, and that equals alpha plus beta s plus alpha, and all this still equals to 1. And now we can break this up into two separate equations. And so this is also the same as writing something like this. Some, let's say 0 times some s, right? And so if it were written this way, it'd be easier to tell that alpha is equal to 1, and this alpha plus beta is equal to 0. And so if we write it that way, then we can easily see that alpha is equal to 1. And when alpha is equal to 1, we can plug it back into the equation. So plug it right back into here and here. And then we get 1 plus beta s plus 1 is equal to 1. And so we get that, if we subtract 1 from both sides, we get 1 plus beta s is equal to 0. Divide by s, we get 1 plus beta is equal to 0. And ultimately that beta is equal to -1. And we can check that alpha plus beta is actually equal to 0. So -1 plus 1 is equal to 0, so that checks out. So now we're given the constants that we need. So we switch colors back here. And now we want to find the inverse Laplace of this partial fraction. So that'd be 1 over s plus beta is now -1 over s plus 1. And I'll just rewrite this a little bit and just do minus. And so here we definitely have these values in the Laplace transform table, and we're looking for now the Laplace transform of 1 over s and the Laplace transform of 1 over s plus 1. And so remember that the Laplace transform is a linear function, so we can actually distribute this Laplace transform to both of these here. So this is equivalent to saying the Laplace transform of 1 over s minus the inverse Laplace of 1 over s plus 1. So if we look and find the inverse Laplace of 1 over s, we see that here's 1 over s. It is the unit step function. So that's u of t. Minus the inverse Laplace of 1 over s plus 1. So 1 over s plus 1 is similar to this one here, 1 over s plus alpha with alpha equal to 1. So that is equal to e to the minus alpha t. So it's e to the minus t. So that's e to the minus t. And the unit step function is 1 whenever t is greater than 0, and we're assuming that t is greater than 0, so the unit step is 1. So 1 minus e to the minus t. And that's our answer there. Y of t is equal to 1 minus e to the minus t. So there you have it. The answer is 1 minus e to the minus t. So this was what seemed to be a pretty simple problem, kind of got ugly in the middle with the partial fractions, but we got to remember to use all the tools that we have in our toolbox in order to solve these problems. Simplify whenever possible. Again, we could have done convolution on this and done a convolution integral, and so it would have been a little bit more difficult. You would have had to do an integral of an exponential, which I guess is not too bad, but for easy functions like these, for which we already know the transforms for, it's sometimes easier to convert to functions of s rather to convolve them. And so that's what we did here. We used knowledge that we are very comfortable with, like voltage divider, and took the inverse Laplace of this voltage divider that we're pretty comfortable working with. So if you guys enjoyed this, please give it a thumbs up, subscribe to the channel, and if there's anything that you'd like me to cover, anything you didn't understand, please feel free to let me know in the comments below. And until then, enjoy engineering.